All right, so a power series is basically, if you look at it, pretty much a polynomial that goes to infinity. It is of this format. It's a summation of a constant times n to the nth power, or times x to the nth power. And it's a power series because x is a variable. So the n actually is going to change based on my terms, where x is going to be able to actually change and based on the problem that I'm looking at. So some values are going to converge, some values are going to diverge. So unlike the problems that we've looked at so far, where they always either converge or diverge, these series are going to converge for a specific set of values for x and diverge for all other values. So we need to find out which values are going to allow us to do that. And that's in essence what we're going to be really looking at tonight, is how to figure out those values. So as you can see right here, the f of x, that's basically a polynomial. It's a constant, then the x term, then x squared, x to the third. It just goes on forever. That's one of the reasons why the power series is so useful, because it allows us to model extremely large polynomials and actually figure out what those values would actually become in certain situations. So that's really one of the reasons why we look at the power series. All right, so let's look at one. So this one right here, it's the summation of and from 0 to infinity of n factorial x to the n power. So we want to find out for which values of x is this series convergent. So you see I have the ratio test here. The ratio test is probably going to be one of the main ways that we're going to determine where things are convergent, because it gives you that range of values. So remember, the ratio test, if the limit is less than 1, it is absolutely convergent. If the limit is greater than 1 or goes to infinity, it is divergent. And if it equals 1, we don't know. And that's also going to come into play when we're looking at some of these problems. All right, so let's look at the ratio setup for this one. So we have the limit as n goes to infinity of n plus 1 factorial x to the n plus 1 over n factorial x to the n. Don't forget the absolute value. That actually does mean something in this case, because x can be any value. Unlike where we were looking at the ends, where it's all integer values from 0 and up, x can actually be anything in this situation. So the absolute value is actually very important when we're looking at this. So we can break this down a little bit. Remember, I can split up that n plus 1 and n factorial. I can also split off the x times x to the n. So I have n factorial in the bottom and x to the n. So now we can cross off stuff that's the same on the top and the bottom. And this is the limit as n goes to infinity. For some reason, I can't keep forgetting the I. N plus 1 to the absolute value of x. And that goes to infinity, because infinity plus 1 is most definitely infinity. So so the question is, does this one converge at all? So basically, this is saying that for all values of x, it would be going to infinity. However, there's one value of x that would not make it go to infinity. What's that value?
0?
Correct. Because anything times 0 would be 0. So in this case, this is only convergent when x equals 0. And it's divergent when the absolute value of x, or when, actually we can just put x, when x does not equal 0. So that ends up being my convergence and divergence for this one. The next one we're going to look at is going to be a little more work to do it. We're going to see it, but this one's a nice one to start off with because at least it gets the idea of how we're going to actually find it. The ratio test is really the one we're going to use quite often for it. And then looking at the answer and saying which direction we got. This one goes to infinity, so pretty much it's always going to be divergent, except in that one situation where x is 0, because a equals 0 at that point. Look at this one. Again, we're looking for which values of x does this converge. So again, same thing. We're going to do our ratio function. So I have x minus 3 to the n plus 1 over n plus 1 times n over x minus 3 to the n. So I can, simplifying this one down, I get n over n plus 1 times the absolute value of x minus 3. Remember, I basically just taken that, this splitting it up into two pieces so I can cancel those out. And the n over n minus n plus 1 doesn't have to be an absolute value because, again, n's are starting off, those are never negative. So if I take the only piece with the n and divide everything by n, this ends up being 1 over 1 plus 1 over n. So that reduces down to 1. So this limit goes to the absolute value of x minus 3. Any questions on how we got that?
So it's just, it ends up becoming 1 over infinity, which is just,
Or actually, no, it doesn't become 1 over infinity. It becomes 1 over 1.
right, because it's just plus 0.
Right.
Okay.
So yeah, it becomes 1 to, which is just 1. So that's how I get the 1 times x minus 3. If it did come out to be 1 over infinity, it would have gone to 0. And then that whole problem would have just gone to 0. In which case, it would have been always convergent because my limit was less than 1. So, all right, but in this case, we've got the x minus 3. So we have to actually figure out what values of x is going to make this work. Remember, the ratio function or the ratio rule says it's got to be less than 1. So I've got x minus, the absolute value of x minus 3 is less than 1, which means that it is between 1 and negative 1 and 1. So if I add the 3 to all sides, I end up getting 2 is less than x is less than 4. All right. Any questions on how I got that? All right, we're not quite done though. Because the ratio, go back, if it's less than 1, it's convergent. So that's, we got that part there. If it's greater than 1, it's divergent. So it would be the opposite of this. However, we don't know what happens when it equals 1. And if we look at this, if I plugged in 2 to this or 4, this would equal 1. So I need to figure out what's going to happen at 2 and what happens at 4 to determine if it's going to be convergent there or not. So to do that, we're going to, let me duplicate this. We know it's convergent from 2 to 4, but we need to figure out if it's convergent at 2 or if it's convergent at 4. So we're going to plug those values in for x and see what the problem looks like. So if I plugged in x equals 2, I got -1 to the n over n. Is that convergent or divergent? That function right there, or that series? And how would we be able to tell? So this one right here, this is an alternating series. It's got -1 to the n. So this one happens to be the alternating harmonic series. So that one we know is convergent. So that means I'm going to put a line under that equal to, because it's going to be greater than or equal to 2. If I plug in 4, I get 1 over n, which I know is divergent, because that's the harmonic series. So it's convergent during those values there, and would be divergent for everything else.
Wait, sir, can you explain again how at x equals convergent?
At x equals 2, it's the
Yeah.
alternating series. We do the alternating series test. This happens
Okay.
to be the alternating harmonic series, which when we did that test, we actually proved that that one works. But we basically just have to show that the limit of it goes to 0. So the limit of 1 over n does go to 0. So that's true. And I'm blanking. And that the series is decreasing. So 1 over 1 over 2, the second one is always going to be less than the previous one. So that series is decreasing. So since it's decreasing and the limit goes to 0 and it's alternating because of the -1 to the n, it's convergent.
All right.
Could you please say that last part one more time, Professor?
So an alternating series test has to be the limit of the series has to go to 0 of the absolute value. So we're just looking at, in this case, 1 over n. So the
Right.
limit of 1 over n, that goes to 0. And it's decreasing, so that b to the n plus 1 is less than b to the n. So whichever number you look at, we can take anything. It's like 1/3 is less than 1/2. So that also checks.
Right, but that's also the case for the one below it.
Correct. But if the one below, it's not an alternating series.
Okay.
So I can't do the alternating series test on this, the second one.
I see.
So
And
remember,
what's the other way for alternating series is to to be written, it's typically -1 to the n, and then the other one was, what was the other one?
It could be -1 to the n minus 1, n plus 1. It just depends on which direction the negative sign goes.
So as long as it's just a -1 to some sort of variable, it's going to be alternating.
Right, because you basically you want the series to go negative, positive, negative, positive, negative, positive, or positive, negative, positive, negative, positive, negative. You want it to constantly switch back and forth. That's the definition of alternating.
Thank you.
No problem. And like I said, the key with this one is you have to do the 2 n pieces. If you don't do the 2 n pieces, then you won't have the final answer there. All right, so for any power series, there's only really 3 possibilities. 1, it converges only when this in essence is 0, which we did in the first set. It converges for all x, which we talked about was if, for example, when we did, actually wasn't that one. I said when it was this one, if that was the value? Was it this one? Oh yeah, when it was 1 over n. If that was just 1 over n and this went to 0, it would converge for all values because it would be just going to 0. So depending on what the thing in front of it is with the n's, it could go to 0 and basically be all values. Or it converges based on a series, which is, or a range of values, which is what we did here. Those are really the only 3 cases, which kind of is self-explanatory because that would be the only 3 cases you could possibly get. It converges on one number, it converges on no numbers, or it converges in a range. So somebody made a lot of money coming up with that theorem that basically says it converges in all possibility cases. All right, let's look at another one. So this one asks for one other piece of information. This one's asking for the radius of convergence. The radius of convergence, so for example, if we look at the last one we just did, the radius of convergence for this one is 1 because it's one space between the 2. So the radius of convergence is whatever the x is going to be basically multiplied by. In this case, it's a 1. So it's 1 space there. Think about radius and diameter. The diameter of this was 2. The radius is 1. So you could figure that part out before you actually do the actual problem and come up with the range. So, all right, let's look at this one. So we're going to do the exact same thing. We're going to do the ratio test. So I've got -3 to the n plus 1, x to the n plus 1 over the square root of n plus 2 times the square root of n plus 1 and x to the n. Everybody see where I got the n plus 2? All right, so now we can simplify this down some. So I'm going to put the square roots on top of each other. So I have square root of n plus 1 over n plus 2. I'm going to have -3 and x left over. So if I divide everything in there by the 1, this limit ends up going to 3 absolute value of x. Because remember, we're basically dividing this whole thing inside by n, which means that comes out to be 1. I can take the absolute value of -3, which makes it the 3 out in front. Any questions to that point? All right, so now we've got to look at my my convergence range. So I've got 3 absolute value of x has to be less than 1. So that means the absolute value of x has to be less than 1/3. That's my radius of convergence. My radius of convergence is 1/3. Because it's basically whatever that value right there is. Now my range will be 1/3, or -1/3 is less than x is less than 1/3. So that is going to be my range, or my interval. All right, so we now have to test each of those cases, the -1/3 and the 1/3. So when x is -1/3, I get the summation of n equals 0 of -3x, and then -1/3 x is just -1 to the nth power. Oh, sorry, +1 to the nth power. So it's just 1. That ends up being just 1 for the -1/3 over the square root of n plus 1. Now, I can make one little modification to this. Does everybody see what I just did there? Because this is actually kind of important when we're looking at this situation, because it's going to make my life easier to figure this out. So the initial problem, I had the n plus 1, which means I have to do extra work because it's not just like a p-series or something like that. However, my n started off at 0. So if I say my n starts off at 1, is this series and this series going to give you the exact same thing? Yes, because if I plug in a 0 there, I get the square root of 1. If I plug in a 1 there, I get the square root of 1. So these two series gives you the exact same thing. This one right here is now a p-series with the p equaling 1/2, which is less than 1. So that diverges. Questions with that?
Professor, I'm a little confused as to where the numerator went at the beginning there. You just have a
So-
one. What was
So
the
we
logic
get,
there?
so you have negative 1/3, so you have -3 to the n times -1/3 to the n. That's -3 times -1/3 to the n, which is 1.
Got it.
All right, so we've done the -1/3. Now I have to do the 1/3. So if x equals 1/3, I'm going to have the series of n goes to, or n,
It's just going to be an alternating series, right?
correct. Yep, that's going to be -1 to the n over the square root of n plus 1. Which we, again, if we want, we can easily switch this to, I can do -1 to the n plus 1 over the square root of n, just to clean it up a little bit. This is an alternating series now. So if we look at it as an alternating series test, the limit as n goes to infinity of 1 over the square root of n, that does go to 0. And the second part is b to the n plus 1 less than b to the n. So if we look at it, we have 1 over the square root of 3 is less than 1 over the square root of 2. That is also true, or equal to, I should say. So it fits both those criteria. So this is convergent at that point. So we've got the other way you can write this, because they do show this to you in 2 different ways. You can write this in interval notation as well. So this is interval notation. The parenthesis is represented by the as just less than, and then the bracket means it's equal to that. So you can see that as 2 different ways. So if the question asks you to write an interval notation, that's what it means as interval notation. So they both mean the exact same thing. Just the key is remembering what the parenthesis and the bracket is. The bracket, it means the equal to, the parenthesis is not. All right, let's do one more. So we've got, again, limit equals to infinity, n plus 1. So same thing. If I simplify this down, I'm going to end up with n plus 1 over n. And then I'm gonna have a 3 in the denominator. And the absolute value of x plus 2. So this goes to 1/3 the absolute value of x plus 2, because this first part goes to 0. Or not 0, 1, I mean. Sorry. All right, so I have 1/3 the absolute value of x plus 2 has to be less than 1. So that means the absolute value of x plus 2 has to be less than 3. So my radius is 3. All right, so now let's find my interval. So I've got -3 is less than x plus 2 is less than 3. So subtract 2 from all the sides. So -5 is less than x is less than 1. So I've got that for my interval. So we've got that as my interval right now. But again, we still have to test the -5 and the 1. So if x is -5, I get n -3 to the nth over 3 to the n plus 1, which ends up being -1/3 n. So if I want to modify that a little bit, so it looks a little better, I can pull out the -1/3 there, leave it as -1 to the nth power. Sorry, that was to the nth power times n. So it is an alternating series, correct? So if we look at my alternating series tests, remember I always say do the limit part first. So the limit is n goes to infinity of n goes to infinity. So it fails the first test. And what was the rule if it fails the limit part of the alternating series test? Am I done or do I have to do something else? Nice thing in this case is I'm done, because that means it passes the test for divergence. Because the test for divergence says that the limit of n as n goes to infinity goes to anything other than 0. So since it goes to infinity, it is divergent. Now let's look at x equals 1. So I've got n three to the nth over 3 to the n plus 1. So I get the 1/3 again, and it's just n. That right there automatically fails the test for divergence because the limit as n goes to infinity, n is infinity. So that's my answer there, or as an interval, it would be -5 to 1. All right, any questions with power series? So the only difference between these and what we've been doing is you have to find a range of values that could possibly work. But the tests you're going to use will still end up being the same tests. You're going to use the ratio test for quite a bit of it, and then you're going to have to use other tests to figure out if the endpoints work. All right. Look at the other direction of power series. So the other thing that I can do with power series is I can take a function and represent it as a series. So I know that 1 over 1 minus x equals that there. Now, somebody's going to say, well, how do we know that? Because this right there is a geometric series. And remember, the geometric series of a r to the n goes to a over a minus r. So that was the geometric series. So if I change and just let that as x to the n, this is going to converge to 1 over 1 minus r, because a equals 1, x, and r equals x. So all I'm doing is I'm taking that geometric series, and instead of having the r, I'm making it an x. So one of the things,
Sorry to interrupt. That doesn't seem. I might be missing something here, right? But as n goes to infinity, right? Those numbers get bigger and bigger and bigger on the left expression, but on the right expression, the numbers get smaller or negative. So how are they equal? I mean, is proving this outside the scope of this class?
okay, so no, actually, I'm going to show you this in a second. But I want to, I'm just trying to clarify what you're saying. So this side of the equation, right? So this part over here, you're saying is getting bigger and bigger.
No, I'm saying on the sum of AR to the N, if you just think that that was just the geometrics, yeah, that.
Okay, that
that-
doesn't always get bigger though. Remember, it depends on what R is. So in a geometric series, if the absolute value of R is less than 1, it converges. Which is why that's there.
Mhm.
So it really depends on what R is. It depends on what my ratio is. So you're right. If my ratio, if R was 2 or 3 or 4, that's going to go to infinity. Absolutely. But if R is 1/2, it's going to converge. That was why the geometric series was so important, because that was a test that we used for convergence. If that ratio was less than 1, we can have it converge.
Okay, and are you, I mean, is the proof simple enough to go through where AR to the end can be expressed as A divided by?
Yeah, we did that a while ago.
Okay,
We did that back in section 11 too. So not going through that again tonight, but yes, if you go back to the section 11.2, it's got the proof in there, or if the notes you can actually see.
okay.
But that was the entire purpose of doing the geometric series, is that it actually does converge to a very specific number. And because we know it converges to a very specific number, if you look at this piece up here, that's an infinite polynomial. So we can use this series here to actually basically come up with a series and then do the rules of calculus and everything else to come up with what that series is. So it allows us to do it allows us to integrate some functions that we couldn't normally integrate. It allows us to, that's not what I wanted to do. It allows us to find convergent points for series or for functions that we wouldn't have had to known beforehand. So it's a very useful piece of information to be able to do, as long as I can make it fit into this geometric series or to a series that I know. So we're doing the geometric series, but this isn't the only one that would work. As long as you can take any series that you have that you know goes to a very specific value, you can do this with. The only one that we know off the top of our heads that we've done is the geometric series. So that's why we're focusing on this one. So this piece right there is what we're going to use again. All right. So let's look at this series. So I have 1 over 1 plus x squared. So what I want to do to make this work is I need to change this into this. So I need to figure out how I'm going to modify. Actually, my arrow's wrong way. I want to change that into that. I want to figure out what I need to do to modify this to become this. So the first thing I'm going to do, so if we look at it, we can say, okay, this part right here, it's got a plus. So 1 over 1 plus. So actually, so I can change that to that, right? Are those two things the same? Yes or no? Okay, I'm gonna take that as a yes. So if 1 over 1 minus x is this, this one, 1 over 1 minus negative x squared, is negative x squared to the n power. So as long as I can get it this side into that format, I can modify this side as well in the same way. It's basically kind of like doing a U substitution. I'm just saying, well, that is changing that, so that has to change to that. Does that step make sense? All right. Now, we got to clean this up a little bit so I can actually do a geometric series to it. So we can change this to, I can pull out the -1 to the nth power, and then this becomes x to the 2n. So this is the final series that we've got there. The second part of this question is, what does it converge to? So remember, this one up here converges as x is less than 1. So this is going to do the same thing. This is going to say the absolute value of negative x squared is less than 1. So I've got x squared is less than 1. So that means -1 is less than x is less than 1. Is my interval on when this is going to converge.
Professor, could you please repeat the last 30 seconds of that there? I was able to follow to absolute value of negative x squared is less than 1. And then what was the next step?
Actually, we do it real quick. I'm going to clean up this a little bit so it's better note. All right. So my new series was 1 over 1 minus, or actually, let's do it. So I've got the absolute value of negative x squared is less than 1. So absolute value takes care of the negative sign. So, and x squared can never be negative. So I know x squared is less than 1. So if I do the square root of both sides to get rid of it, I have x is less than plus or minus 1, which is -1 is less than x is less than 1. The other way you could have looked at it as, instead of doing the square root, you could have just said the absolute value of x is less than 1. That also would have worked. So either one of those, both mean the exact same thing and both come out to be the exact same range, in which case my interval can also be written like that. Unlike what we did before, we don't have to test the endpoints. Because in a geometric series, if it equals 1, it diverges. And we know that. We didn't do the ratio test, so we don't have that ambiguity part. All right. So in essence, what we did, the entire goal of this was we took the function 1 over 1 plus x squared. So that was my f of x. And I've now said my f of x equals that. So it gives me another representation of the function. Of which now we can use the rules of series to figure out values instead of just the actual equation. Yep. All right. Let's look at this one. So I've got x to the third over x plus 2. And again, remember, I'm trying to get it to use this setup. So I need to change it into that setup in there. So if I look at, when we're doing these problems in this function, in this series right here, is the x a constant or is the x part of like the actual thing that's changing in each term?
The x is a constant.
Right. So now, what can we do with constants in series?
Pull them out.
Right. So I can change this to x to the third times 1 over x plus 2. Because this piece right here, that part right there, is a constant. Because it's not being raised to the nth power or anything else like that. It's actually just to the third. So I can pull that x to the third right out of the entire problem to start with. And I don't need to worry about it in terms of that actual piece up there. So we're going to leave that x to the third alone for a little bit. And we're just going to deal with this 1 over x plus 2. So the first thing I'm going to do is I need to get this to be 1 minus x. That's my goal. So if I just look at the 1 over x plus 2, first thing I'm going to do is I'm going to change it to 1 over 2 plus x, because I want the x second. And then I'm going to pull out a 2. So I'm left with 1 minus or plus 1 over 1/2 x, like that. Because again, the goal is to get it to look like this. So the first thing I did is swap it around so the x was second. And the second thing I did was I want to get that 1. So I now have that 1 there. So I have the 1/2 out. I can take that whole thing out there, so I don't have to worry about that 1/2. I have 1 over 1 plus, or actually, let's change the sign, minus negative x over 2. Everybody see what I did there? So again, my goal is to get it to look like that. So now I have the 1 on top, a 1 minus, and then the term for my x. So now I can take my other side and actually write it all out. So I'm going to have x to the third. So 1/2 x to the third summation 0 to infinity of negative x over 2 to the nth power. All right. Questions with that? All right. So the next piece we have to figure out is my interval of convergence. So we're going to take that, the absolute value of negative x over 2, and that's got to be less than 1. So I can pull out the negative sign disappears, and I can pull out the 1/2. So the absolute value of x has to be less than 2. So my interval is negative 2 to 2. All right. So we've now rewritten this function in terms of a power series. And we have our interval of convergence. So far, the 2 examples we did, we basically just rewrote what they gave us. As long as we do the same thing to both sides, we can do a lot of things to it. And what we're going to look at now is actually looking at one more step. We're going to look at it in terms of we can do an integration or a differentiation. So if I do the derivative of both sides, that actually will also work to rewrite the function. Or if I do the integral of both sides, I can also use that to rewrite the function. So, but again, everything we're looking at is trying to go back to that original function that I have. Because I know that derivative or that geometric series works. So when I'm doing my integral or my derivative, I'm looking at it in terms of that part. So, back to the thing before I switch slides again. All right. So we have that. And I have this. So when we're looking at this series right here, the 1 over 1 minus x equals that. If I did the derivative of this, if I had f of x is 1 over 1 minus x, what would f prime of x be? So if we look at this in terms of a quotient rule, which we actually kind of know, we could actually look at this in terms of, we could do this. If I do it with that, I can actually do it as a chain rule, might make my life a little bit easier. So what is the integral of, or the derivative of 1 minus x? It's just 1. And then I'm going to do the derivative of that. So I would take the -1 down, and it would be 1 minus x to the -2nd power. Oh, sorry, that's -1. So the derivative of this is 1 over 1 minus x squared. So the derivative of that is that. Everybody see that? Okay. So if I did the derivative of this side over here, so I did the derivative of this side. So now I have to do the derivative of the other side. So that's going to be n x to the n minus 1. If I did that as a derivative. So what that gives me is that function meets up with that power series. And my radius stays the same. So in this case, my radius is still, or my interval is still the same. So x is less than 1. So my interval will be -1 to 1.
Professor, still a little confused on the representation there of well, what you put in the square box there. And
So we
times
did,
size.
okay, so I said that, I said the derivative of this piece up here. So if I said the derivative of this is that, correct?
Okay,
That's what I did down here. So I did the derivative of one side and I got the new piece. So now we're gonna do the exact same thing on the other side. So I'm gonna take the derivative of that equals that. You bring the n down, you subtract one. That's,
oh, okay,
so since I did the derivative of both sides, those two things are now are equal to each other
got it.
based on this theorem. All right, let's look at this. All right, so in this one, we've got ln of 1 plus x. So again, we're going to go back to, we still have to use this. Still using that. So if I have ln of 1 plus x, and I want to find what we're doing, or using this, I happen to know that this equals the integral of 1 over 1 minus x. Oh, sorry. 1 plus x, not 1 minus x. So that's the integral of 1 plus x. Does that make sense? So since I know that's the integral of 1 plus x, I need to figure out the other side. Well, first of all, that's 1 over 1 minus x, not 1 over 1 plus x. So then I'm going to change that a little bit. So I'm going to do that's one side. And I'm going to do the integral on this one. And that x is going to be minus x. So this becomes the integral of summation n equals 0 to infinity of negative x to the n. So we can do just the integral of the inside piece. We don't need to do the integral of the summation. So I can change that to the summation of n goes to 0 of the integral of negative x to the n. So to do this, so I've got
I think I understand why it's negative x to the n, but could you please just kind of,
because it's 1 over 1 plus x is 1 over 1 minus negative x. So that changes the summation to negative x to the n.
thank you.
No problem. So if I do the integral of that, that piece over there, I get -1 to the n minus 1 x to the n over n. Oh, actually, let me rephrase it. I get -1 to the n times x to the n minus 1 over n minus 1. That's better. So I'm gonna actually change this to get rid of all those -1s. So I'm just gonna start this off at 1. Cleans up the mess. To x to the n over n. Oh yeah, and don't forget the plus c. So I have ln of 1 plus x equals the summation of this. X to the n over n. If I plugged in 0 to x, what would the ln be? If I plugged in 0 on the right side, I mean left side, sorry, what do I get?
1.
You get ln of 1, which is
0.
0. So that c equals 0. Because that would balance out the side. So if this is 0, this would actually end up being 0, because if I plugged 0 in there, that whole side's 0. So, oh, and then the range stays, the interval stays the same. X is less than 1. So basically what we looked at is we looked at the ability to, for a power series, to actually take it and do the integral to them to modify the equation, the derivative to it, or we can look at manipulating the equation algebraically to change it into a power series. So those are the 3 ways that we can do it.
Professor, I'm having a little trouble on the final statement there. So where did we get the n minus 1? I thought it was an integral, so we'd be adding 1, not -1.
You are, but it's, so the n minus 1 is coming from, actually, yeah. So it's because you're bringing it down. So it's because the n was in the denominator, because there's a -1 to the nth power here. Because this right here is really the integral of, actually, this is really the integral of -1 to the nth power, x to the nth power.
Uh-huh.
So it doesn't actually matter when I'm bringing the n down and subtracting 1. It doesn't change the problem. That's why I didn't do it. It's still, because in essence, because remember that -1 is really just doing the alternating, going back and forth.
Uh-huh.
So that's a constant, which I can bring out. I can bring out that -1. So when I'm doing the integral, I don't need to worry about the n. I can actually bring that out as a constant. That's why it's just there. So I'm really just doing the integral of x to the n, where the -1 to the n is coming out front.
Okay, yeah, I get that, but how do we, why is it being represented as in the middle there, directly to the right of the summation of -1 to the n times x to n minus 1 over n minus 1?
That's it. Okay, hold on. Let me. I'll write it out a little, so I have a little more room to do this. I know what you're asking. All right, so in this case, I'm pulling, so all I'm really doing is I'm doing the integral of negative x to the n power. So that's the integral of -1 to the n power, x to the n power, which is -1 to the n power integral of x to the n, which is -1 to the n power x to the n minus 1 over actually it's n plus 1. It was
That's what I've been,
there you go. I screwed up the plus 1. That would be where I messed up. Yeah. So it should be a plus 1. So it wasn't the n, it wasn't the -1, it was actually the n. That was the mess up. Yeah. So your summation was, I put the -1 to the n back in, x to the n plus 1 over n plus 1. And then I just changed it to, instead of 0, I started off at 1. So that's how I get the n minus 1 x to the n over n. So we have that, and then we changed it to that. I had derivatives on my head because I was doing derivatives before that one. Not better. And on that note, we're done.